Thank you. Dan, I'm glad that you brought up Almahata because I like to try to remind the community about the fact that Almahata could be what we will find on the surfaces of Bennu and Ryugu. It's not the most likely case, but we can't forget about it. This is work we've been doing for about 7 years now. We've been looking, we have a spectroscopic survey that we called now I'm blanking out on the name of my own survey. It's called PRIMUS. It's the Primitive Asteroid Spectroscopic Survey, and we have a number of collaborators. We use telescopes all around the world, and so the outline of my presentation is I'm going to tell a little bit about dynamics, thanks to Bill. We're going to tell you about spectroscopy, and then I'm going to tell you about the implications for Bennu and Ryugu and the conclusions. But just in case you need to go to the next session, here are the conclusions. And the main point is that we've done now a survey of 4 families in the inner belt, actually 5 families in the inner belt. And the inner belt primitive asteroids break into 2 groups. The Eragone-like that all have a 0.7 micron feature, or not all, but the great majority, and they're spectrally diverse. And the Polana-like, which have no 0.7 micron feature and are spectrally homogeneous into C and B types only. Both sample return targets, Bennu and Ryugu, do not show that feature from ground-based observations and are dynamically more likely to come from the Polana family. So both spectroscopically and dynamically, we believe they're related to the Polana family. By the way, the lack of a 0.7 micron feature does not necessarily mean that there is no hydration. But what I wanted to bring up is the fact that 2008 TC3, the parent body of Almahata Sitta, also originated in this part of the asteroid belt, and it's possibly related to the Polana family. So we need to keep this in mind, and we will have a chance to do so next year when both Hayabusa 2 and OSIRIS-REx get to their targets. And then the other thing that I wanted to bring up is the fact that the background objects seem to be spectrally similar to the family. So when we're studying the families, we're basically sampling everything that is there. The background does not seem to be spectrally different from the families. As we know, or we may know, that the main source region for most NEAs is the inner belt through the new 6, if you look at the asteroid belt, the inner belt is the area that's going to be providing most NEAs, and most of them are going to be coming through the new 6, which is here, this curved edge to the inner belt. And here we have asteroids of different albedos, and in the inner belt we have both high albedo and low albedo asteroids. The low albedo asteroids are the families that we've been studying. And both Bennu and Ryugu are low albedo asteroids, primitive asteroids, and most NEAs have a retrograde spin, which is consistent with them coming from the inner belt through the new 6. So both the rotational properties and the dynamics are telling us the same thing. But where in the inner belt are they coming from? So the inner belt has several low albedo families and a background and where these NEAs may have originated. And so we have here the main families that Nesvorny has identified. In the inner belt we have Polana, Eragone, Sulamitis, Clarissa, Clio, and Chaldea. And we have published papers on all of these, and then there's actually another subfamily of Polana called Eulalia. We've studied all of these, and you notice that if in this plot, this is the background of low albedo objects outside the families. So these are the ones that Nesvorny has not classified into these families. But if you look at the morphology of this, it's very clear that the background has the same shape as the family. So by studying the families, we're essentially also sampling the background, but we are also going to sample the background spectroscopically to make sure that this is indeed the case. So what about spectroscopically? What are our results? This is PRIMUS, as I said, and so far we have observed Polana, Eulalia, Eragone, Sulamitis, and Clarissa. And most NEAs have a retrograde spin, which is consistent with them coming from the inner belt through the new 6. So both the rotational properties and the dynamics are telling us the same thing. Polana has the following characteristics. It is the largest in the inner belt. It is spectrally homogeneous. You only find C and B asteroids. And it has basically none of its members have a 0.7 micron feature. So is it anhydrous? Well, not necessarily. You can have no 0.7 micron feature and still have a 3 micron feature. We can discuss that offline if you want to. But our initial results are in these two papers. And but the spectra of Bennu and Ryugu are actually compatible with both Polana and Eragone. Why? Well, Polana, as I mentioned, it is spectrally homogeneous and has C and B types. Ryugu is C and Bennu is B. And so here are results for Eragone. So Polana could be the parent of both. Eragone could also be the parent of both because even though dynamically it is not as favored, it has B-type asteroids and it has C-type asteroids. Most of them show the 0.7 micron feature. About 1/3 of the Bs and essentially all of the Cs. And so we have also that result published. And so in terms of the two spacecraft targets, we have that they are favored to come from Polana both dynamically and spectroscopically because they are C and B, which are in Polana, and because there's no 0.7 micron feature compatible with Polana. Again, we could see that hydration once we get to them, but these are the results right now. And what about the other families? So we have studied and published Eragon, this is Sulamitis and Clarissa, and Sulamitis looks like Eragone, and Clarissa looks like Polana. So the primitive families in the inner belt are falling into these two different spectral groups, the Eragone-like and the Polana-like. So Clarissa is just like Polana, Sulamitis is just like Eragone, and these two papers have been accepted. And so where do Bennu and Ryugu come from? Well, we think they come from Polana, but understanding their source and linking them to one of these families is going to help us put into context both the in situ and the sample return from both of these missions. What next? My warning about Alma-Hatasita and TC3, this object probably came from the Polana family, so it could be that Bennu and Ryugu are very, very heterogeneous, and that's something we should be ready for, and in OSIRIS-REx we're planning for. I'm sorry, I'm going to back up for a second. And so in terms of our observational program, our next two targets are the Clio and Chaldea families, and then we're also going to be studying specifically the background outside of these families to compare with the spectra of the families. So here are the conclusions again. Thank you.
We have plenty of time for questions.
Oh, I'll go to Dave first. We'll get you second.
Okay, this is a little bit off topic, but fill me in on some basics here, Humberto. Can you, from the sizes or shapes of the families, can you infer anything about the collisional regime that disrupted them, or what the relative sizes of the disruptor and the disrupted asteroid was?
Yeah, I could, but this is work that is done by dynamicists, and some of my best friends are dynamicists. Anyway, no, but it seems like Polana was not disrupted as much as Themis, for example, and that's the work of Seth. What's Seth's last name? I forget.
Jacobson. Seth Jacobson?
Jacobson, yes. And he's, anyway, he did work on this, and spectroscopically, it also looks like Polana was not disrupted, or at least it was not differentiated as much as Themis was in terms of the spectral the spectral characteristics that we have in the family. Eragone is a younger, smaller family. I don't know if the dynamicists have done estimates of the size of the impactor and the size of the parent body. That's
I think that Polana and Eragoni both had both their parent bodies were over 100 kilometers, what precisely they were. And so to break them up in each case, you're probably looking at getting hit by maybe 20, 30 kilometer body, roughly. Might be larger. I'd have to go back and look at what I wrote back into 2015. So, let me go to Amanda.
Just because you said you wanted to talk about it more, I wanted to ask you about the 0.7 micron feature, not necessarily meaning that the surface is anhydrous. Is that based on a 3 micron?
yes, and
signature?
Andy
Okay.
can tell you more about this.
Yeah.
But in
I don't
about,
disagree, I just wanted to.
Yeah, it basically, you can have an absence of 0.7 micron feature, and in about half of the cases, there will be a 3 micron feature. So something can either erase the feature or they would never have shown, but there is still hydrated minerals there.
The 3 micron feature might be more robust.
Yes, it's also much more sensitive, if you can observe it.
More questions?
Okay.
I'll just make a brief comment on something, which is, I think everything you said is certainly fine from a dynamical perspective. The one thing is that Bennu is small enough, like a half a kilometer in size. We don't really have good constraints on how those objects move by Yarkovsky and the rest. We can make estimates and we can sort of extrapolate our models, but until we actually know that, we can't completely rule out Eragoni. I'm like you. I don't think it's a likely
I'm not
candidate.
ruling it out. Yeah.
Yeah, but I think it's. Yeah, I mean, we should be careful because
Yeah.
we might be surprised.
And
So-
we're observing objects that are at the smallest object that we've observed is about 7 kilometers.
Yeah.
So, and we're comparing with something that is more than an order of magnitude smaller. So
Yeah, it'd be nice to get better constraints on that from a dynamical perspective, from a spectroscopic perspective. Yeah.
Yeah.
So I think it's discussion.
Yeah, thanks everybody. We're exactly on time, which is perfect.